Right now, somewhere in Virginia, a building the size of 4 football fields is sitting empty, finished, wired, stacked with NVIDIA GPUs worth more than some countries' annual defense budgets, and it cannot turn on. Not because something broke, not because someone forgot a permit, because the local power grid looked at how much electricity this thing needs and essentially said, yeah, no, get in line. That line, by the way, is currently 7 years long in parts of the United States. This is the part of the AI gold rush nobody puts in the press release. Companies will spend $3 billion on a data center, ship in 40,000 GPUs at $40,000 each. Build custom liquid cooling loops that push refrigerant through copper pipes at pressures that would make a plumber nervous. And then discover that the actual bottleneck is a transformer, a steel box full of oil and copper wire. Technology from the 1880s. So let's talk about what it actually costs to own one of these things, and why the math is so much weirder than you think. A traditional data center, the kind that ran your email and streamed your shows for the last 15 years, pulls maybe 5 to 10 kilowatts per rack. A rack is basically a tall metal shelf full of servers. 5 kilowatts is a big household, you can plan for that. Utilities can handle that. An AI training rack, one loaded with the latest NVIDIA hardware, pulls 40 to 100 kilowatts per rack. One shelf of computers now eats more power than a city block of houses. And a serious AI data center doesn't have 10 racks. It has thousands. A single large AI campus can demand a gigawatt of power. That is a nuclear power plant. That is a mid-sized coal plant running at full capacity around the clock every day, just so a company can train a model that writes slightly better emails. The global numbers are staggering. Data centers worldwide used roughly 485 terawatt hours in 2025. The IEA projects that figure nearly doubles to around 950 terawatt hours by 2030. AI. Specific facilities are driving a disproportionate share of that growth. We are not talking about a gentle upward curve. We are talking about an energy demand spike that looks like the chart fell off a cliff in the wrong direction. So you think the problem is simple. Build more power plants, burn more gas, spin up more solar farms. Problem solved, cute idea. Here's what actually happens. You are a tech company, you V-picked a site, you V-poured the concrete, you call the utility and say, I need 300 megawatts delivered to this address by next year. The utility laughs, not metaphorically, they actually laugh, because 300 megawatts is the load of a small city, and the substation feeding your area was designed in 1997 for a suburban office park and a Costco. Getting that power to your building requires new high-voltage transmission lines. Those lines need easements. Permission from every landowner whose property they cross. Each easement is a negotiation. Some become lawsuits. The transmission lines connect to substations that need giant transformers. These transformers are custom built, mostly overseas, and the lead time for a large power transformer right now is 2 to 4 years. 2 to 4 years for a single piece of equipment that weighs as much as a blue whale. Then there is the interconnection queue, the formal process for connecting a new power source or a new large load to the grid. In the United States alone, there are over 2,000 gigawatts of generation and storage projects waiting in that queue. The median wait time has stretched past 5 years. Your data center, which took 18 months to build, now sits in a line behind wind farms, battery projects, and other data centers, all fighting for the same limited grid capacity. The building is done, the GPUs are depreciating, and the power isn't coming. This is where the economics turn inside out, because a GPU that isn't running doesn't just fail to make money, it actively loses money. NVIDIA's latest hardware costs tens of thousands of dollars per chip, and a new generation comes out roughly every 18 months. Every month, the GPU sits idle waiting for power. It is losing value like a new car driven off the lot. Except this car cost $40,000, you bought 10,000 of them, and the dealership just announced a faster model. The pressure this creates is insane. Tech companies have started doing something that would have sounded completely unhinged 5 years ago. They're becoming energy companies. Microsoft signed a deal to restart a unit at 3 Mile Island. Yes, that 3 Mile Island, to get dedicated nuclear power for data centers. Amazon has been buying nuclear-powered data center campuses directly. Google signed agreements for small modular nuclear reactors that don't exist yet. Meta has put out requests for proposals seeking nuclear energy partnerships in the range of 1 to 4 gigawatts. These are software companies. Their core product is code, and they are now negotiating reactor fuel contracts and hiring nuclear engineers. Because the GPU is useless without the megawatt behind it, and the megawatt is the thing you can't just 2-day ship from a warehouse. The operational economics compound this pressure. Power isn't just necessary to run the chips. Roughly 30 to 40% of a data center's total energy goes to cooling, removing the heat those chips produce. An AI GPU doesn't just use more electricity than a traditional server. It converts almost all of that electricity into heat. A 100 kilowatt rack is basically a 100 kilowatt space heater that occasionally does matrix multiplication. Traditional data centers used raised floors and big fans. Cold air goes in the front, hot air comes out the back, giant air conditioners deal with the rest. That worked fine at 5 kilowatts a rack. At 60 or 80 kilowatts, air cooling hits a wall. Air simply cannot carry heat away fast enough. The chips throttle themselves to avoid melting, and you've just spent $40,000 on a processor that is deliberately running slower because the room is too hot. So the industry has moved to liquid cooling. Pipes run directly to the chip. Coolant absorbs the heat, carries it to heat exchangers, and dumps it outside. Some facilities use direct-to-chip cold plates. Others submerge entire servers in tanks of dielectric fluid, non-conductive liquid that pulls heat right off the components. It works. It also means your data center now has the plumbing complexity of a chemical plant. More pumps, more failure points, more specialized maintenance, more capital expenditure. The cooling infrastructure alone can add 30 to 50% to the construction cost of the facility, and all of that cooling still needs electricity to run. So here's the actual economic equation of owning an AI data center, stripped of all the investor deck poetry. You need land, you need a building, you need GPUs that cost hundreds of millions of dollars and depreciate like bananas. You need a cooling system that is basically an industrial refrigeration plant. You need power, a lot of it, continuously with contractual certainty, and you probably can't get it from the grid in time. So you need to either sign a long-term power purchase agreement at a locked-in price, which means you're betting that electricity rates won't drop below your contract price for 15 years, or you need to invest in your own generation, which means you are now, congratulations, an unregulated utility with a sideline in artificial intelligence. The power purchase agreements alone reveal how distorted this market has become. Companies are signing deals at prices significantly above the prevailing wholesale electricity rate because the alternative, waiting for grid interconnection, would leave hundreds of millions in GPU hardware sitting dark. They're paying a premium not for cheaper power, but for faster power. The most valuable commodity in the AI infrastructure race isn't silicon or rare earth metals. It is the ability to flip a switch on a specific date. Wait, a $5 billion industry is being held hostage by the delivery schedule of transformers and the availability of transmission line easements. We landed robots on Mars, but we can't plug in a building. Incredible. Just extraordinary work by everyone involved. The financial risk profile is unlike almost anything else in tech. A traditional cloud data center has reasonably predictable demand. Enterprises sign multi-year contracts. Utilization rates are manageable. But AI training workloads are spiky, enormous, and hard to forecast. A single training run for a frontier model can consume a cluster of thousands of GPUs for months, burning through megawatts continuously. If the customer cancels the run, or if the model doesn't converge, those GPUs sit idle and the power bill doesn't stop. The meter keeps spinning. The loan payments on the building keep coming. The PPA still charges you for power you committed to buy. And the GPU refresh cycle makes the capital structure even more brutal. You finance a facility around the current generation of hardware. 18 months later, new chips arrive that are twice as efficient per watt. Your customers want the new chips. Your old chips, which you're still paying for, are suddenly worth half as much on the resale market. You either eat the depreciation or spend another few $100 million upgrading, and each upgrade might change the power density per rack, which might change the cooling requirements, which might mean you're plumbing the building. This is why the unit economics of AI data centers hinge on utilization rate more than anything else. A facility running its GPUs at 90% utilization can generate enormous revenue. The same facility at 50% utilization is a money incinerator shaped like a warehouse. And utilization depends on demand for AI compute, which depends on whether the current wave of AI products actually generates enough revenue for customers to keep buying compute time. Which nobody knows for sure. The companies making the biggest bets are essentially wagering that AI compute demand will grow faster than supply for the next decade, if they're right. Whoever has the power, the chips, and the cooling running first wins the entire market, if they're wrong. If demand plateaus, or if efficiency gains reduce the compute needed per task faster than expected, then there will be very expensive buildings in rural Virginia and West Texas sitting half empty. Their copper pipes full of coolant with nowhere to go. Their 20-year power contracts still billing monthly. Some of these companies are now vertically integrating in ways that would make a 1920s industrialist blush. They redesigning their own chips, building their own power infrastructure, manufacturing their own cooling systems, and negotiating directly with fuel suppliers. A company that started by indexing web pages is now effectively an energy conglomerate, a semiconductor design house, a real estate developer, and a mechanical engineering firm, all to support the ability to multiply very large matrices slightly faster. The thing that makes this genuinely different from previous infrastructure booms is the speed mismatch. A data center can go from blueprint to operational building in 18 months. A new gas plant takes 3 to 5 years. A new transmission line takes 5 to 10. A nuclear plant takes 10 to 15, if it gets built at all. The industry that needs the power moves at software speed. The industry that provides the power moves at concrete and steel speed. That gap doesn't T-close with money. You can T-bribe physics into curing copper faster or training linemen in half the time. So the richest companies on earth are throwing hundreds of billions of dollars at a race where the finish line isn't who has the best algorithm or the smartest researchers. It is who can get a power transformer delivered to a muddy field in Texas before their GPUs turn into expensive paperweights. The entire AI revolution, every chatbot, every image generator, every autonomous system depends on whether someone can run a wire from point A to point B and keep the lights on. The most advanced industry humans have ever built is currently bottlenecked by the same thing that bottlenecked